In the previous section, we looked at integrating functions where we explicitly knew the relationship between the independent variable, or variables, and the dependent variable, and we were able to use numeric quadrature and make that explicit function in MATLAB, and then use integral, integral2, etc. In this section, we're going to talk about functions where we don't know what the relationship is everywhere for the independent variable and the dependent variable, but we're going to be taking and collecting data in time. So, to illustrate that difference, using methods from the previous section, if we knew the acceleration of an object as defined by some function, we can integrate that and get its velocity. However, in the real world, if we don't know necessarily what is the relationship between time and the acceleration, we're going to be measuring the acceleration of our object at specific instances of time. And if we wanted to know what the velocity of the object was, or really estimate what the velocity was, we would need to take those discrete samples that we took and then use a different technique to estimate what that velocity is. The method I'm going to discuss in this section is going to use the trapezoid method for taking empirical data and estimating what the integral of it is. So the basic premise of it is we're going to take our discrete points and we're going to just linearly interpolate between them and connect them with straight lines. And we're going to be able to use this method whether we're sampling at a consistent rate, so if we're doing it, say, 100 times a second consistently, or kind of whenever we're able to get that data, it might not be exactly 1/100th of a second apart. This method will still be fine to use. The one thing we have to keep in mind with our empirical data is we're going to need to know the initial condition or initial conditions in order to fully find what the integral is of our function. And we're not going to be stuck by using the trapezoid rule that I'll get to in a minute. We could use other rules that you may have used in calculus class, Simpson's rule, and other types of rules, which may or may not be better to use. Alright, so briefly how the trapezoidal method is going to work. Well, there's two functions we're going to use out of MATLAB, the traps function and the cumtraps function, to calculate these integrals. But first I just want to kind of point out how is the basic premise of this method working. Alright, so let's say this red line here is going to be the actual function. Let's just use acceleration here as our example. So this is at all points in time what the actual acceleration of our particle was that we're tracking. However, because we have equipment that can't be continuously finding what the acceleration is, we only were able to measure the acceleration of our object at these discrete points x0 through x6. So these will be instances of time. So we only know the acceleration at time 0, time 1, time 2, time 3, 4, 5, and 6. So what we want to do is estimate what the integral is based on only those discrete points. We don't know what really happened between 0 and 1, or 1 and 2, or time 2 and 3. So we're making an estimate that there's just a linear connection between these, even though we can see clearly that that's not the case for this example. So what we're going to do with the trapezoid method is we're going to link together the acceleration measurement we took at time 0 to that we took at time 1 with this straight line. And what we can do is now this forms a trapezoid whose area we're able to calculate, because it's going to be the average of this length and this length, or really the average of this height and this height times this length. So the time between sample 0 and sample number 1 is how we can compute that first area there. And then we can do the second for this second trapezoid that was formed. Again, the average of the acceleration at time 1 and the acceleration at time 2 times this gap in time between x1 and x2. And we repeat that process for every one of these trapezoids that was formed. In this example, or in this illustration, it does look like there's an equal time between x0 and x1, as x1 and x2, as x2 and 3, etc. But as I said before, that does not have to be the case. We can sample slower at some times and faster at others, as long as we know for each trapezoid we're making what its length is there. So the length may vary, and that'll just impact the area that we're going to compute under that trapezoid. Now back to the MATLAB code we're going to use. What we're going to use is either traps or cum traps here. We're going to put our independent variable, which I'll generically call t, because often these are going to be sampled in time, and then the dependent variable y. In the example I was just talking about, those might be our acceleration measurements. So t is a vector of values, and y is a vector of values. If we just use the traps function, we're going to put in that whole vector, and it's going to compute what is the integral under the entire thing, so the total area under the data that we collected. However, if we use cum traps with that same vector, it's going to give us not just one scalar value back, but it's going to give us a vector of values, because it's going to give us what's the integral at the first time sample, the second time sample, the third, the fourth, the fifth, and the sixth. So then we can kind of track, in this example, what the velocity was over the entire time, instead of just finding the velocity at the end. So one thing we're going to notice is that these green areas from the trapezoids are not the same as the actual function. However, again, we only have data from these 7 plots. So we see here that it does a pretty good estimate of the area under the curve between 0 and 1. It's overestimating between 1 and 2. It's overestimating between 2 and 3, underestimating between 3 and 4, 4 and 5, and overestimating between 5 and 6. So we're not able to get exactly the area under the curve, which means that our estimate of the velocity based on these accelerations is not going to be exact, but it's usually going to be a pretty good estimation. Now, what we can do is sample more frequently if possible. So if we did actually know what the acceleration was between 0 and 1, 1 and 2, 2 and 3, etc., we're going to get better and better estimates as to what then the integration is going to be as well. So if we are taking time data, one thing we want to do to improve our results usually is to sample as fast as possible. And we can get a lot more data points in between the 7 that we had here, and then we get a much better estimate as to what the actual curve looks like, and therefore a better estimate as to what its integral looks like. However, depending on the equipment we're using, we might not be able to sample any faster than these 7 data points are, so that would be the limitation, and we kind of have to live with the error that's created when we do this integration.